everybody, it is your old-time favorite obscure scientist here with you today. I'm going to talk about something very different. I'm going to talk about something you've probably never heard of. In fact, if you have your PhD in chemistry, you've probably never heard about this. I'm not going to say it's never been heard of because I've heard of it, and it's possible that you've heard of it as well. But I want to explain this to you. When we teach science, and I don't care what science you're talking about, when we teach science, we lie to you. It's always a lie. It's been said that the art of teaching is the art of telling lies without doing any real harm. Sometimes we tell you lies that are oversimplifications, that are designed to help you get concepts that would otherwise be difficult to explain. Sometimes they're lies of omission. There's a lot of things in science that we never teach. This is going to be one of them. The credit for this work has to go to Dr. Zhonglong Lin, who is no longer with us. He was one of my first two advisors. I started off at Boston College, which is this degree up here. Dr. Udayan Mohanty was my main advisor, and then I also worked with Dr. Zhonglong Lin, who unfortunately passed way before his time. This is called heat of transport. And this is going to be kind of a long, not tram sport, transport. This will be kind of a long video because there's a lot of sort of background information that you're going to need to understand this concept. The reason I'm teaching it, the reason I'm making this video is not because it's going to be important in your life, but it's a subject that I find particularly fascinating. It gives some insight into the way solutions work and ions and whatnot, and things you probably have heard of but never quite put together this way. Before we get started, let's talk a little bit about water, because we're talking about heat of transport in water. Water is, as you know, a very polar molecule, as you probably know. It has an oxygen with two hydrogens. It is a bent molecule, which means that the hydrogens are not sticking straight out, but they're actually at an angle. The angle is roughly 104.5 degrees. Oxygen has a much stronger draw for electrons than hydrogen. We call that electronegativity, which means that the electrons that are shared between the hydrogen and the oxygen are not shared evenly. It's like giving a toy, a very popular toy, to two children. If one is stronger, the stronger one's going to play with the toy more. So the electrons are going to spend most of their time around the oxygen, giving it what we call a partial negative charge. It is not a fully negative charge, because the electrons have not transferred completely. You're not going to let one of those child claim that toy without ever letting the other one play with it. So it's heavier use. The electrons are heavier around the oxygen, giving the charge imbalance. But it's not a complete transfer. But the world is electrically neutral. So if we have a partial negative, and I'm going to do this double negative, something you don't normally see, but this is a really negative oxygen. But the world is electrically neutral, so if the oxygen is partial negative, both hydrogens have to be partial positive. This means that water has a dipole. A dipole simply means opposite charges separated by a distance. They are separated by a distance. Now if you average this out, you have a partial positive charge kind of in the middle of the two hydrogens, partial negative towards the oxygen. We can denote that with an arrow that looks like this. This arrow is telling us that we have a partial positive between the hydrogens, or a partial positive side, and a partial negative side. The arrow always points towards the negative charge, or where the electrons spend most of their time. We can redraw this. This is just a schematic diagram. Everything I'm doing here today is a little schematic. So we can redraw this if we want and symbolize it as a caret. The proverbial caret character, like this. And what this represents is the oxygen at the top and the two hydrogens on the end. And always remember, we have that dipole for the partial positive towards this end, partial negative towards the oxygen. This is what gives water its characteristics. Water is extremely polar. And when we have a liquid, the liquid is more or less, the molecules, the atoms in the liquid are more or less randomly distributed. That's why liquids generally tend to be clear. Not necessarily colorless, but clear. Because there's no regular repeating pattern to diffract light, making it clear so the light can pass completely through it, at least through some pathways. But water is very strange. Water has a lot of randomness, but it also has a lot of order, because this partial positive hydrogen will be attracted to the oxygen of another water. And this hydrogen down here will be attracted to another oxygen here. And so forth. So water, if there's nothing in the water, if it is pure water, yes, there's a lot of disorder to it, and you might remember disorder being referred to as entropy in your thermodynamics discussion. So we'll use that word. It's a poor definition of entropy, but it works for our purposes. So water does have that high disorder as a liquid, but it also has little regions where the water molecules will align themselves in sort of a localized area of high order. Okay? So water is one of the least entropic liquids that science knows of. And there's nothing that says that we can't go in the opposite direction here. So we end up with a sort of highly ordered, because they're all pointing in the same direction, we end up with this little highly ordered part, little highly ordered segment in that otherwise random liquid. It's maybe, experimental studies have shown that it's maybe 6, 7, 8, 9 water molecules large. There's these little clusters, little regions of low entropy. We can actually denote that this way. Where again, the oxygen is at the point, the hydrogens are at the ends. You with me so far? Kind of makes sense. I mean, you probably have never really spoken about this before, but we're not too far out in left field, are we? You can laugh at me if you want to for my use of the chalkboard, but I will always be a fan of chalkboards for just that reason. It's so easy to draw things and then erase them. Anyway, whiteboards, very hard to erase this chalk. This is going to last until it's gone. Whiteboard markers, they dry out quickly, especially if you have someone who doesn't put the cap back on every single time. That dries out those markers. And I used to hate lecturing behind certain professors because they would write something on the whiteboard and then put the cap down and walk around with the marker like this, letting it dry out. Well, the solvent that's holding that liquid in there, that's holding the, it's highly volatile. So it's drying the entire time. And sometimes I will come and find the marker set down without the cap. That's why when I taught and they had whiteboards, I always bought my own damn markers. Then that stupid professor can deal with the dried out markers that they themselves created. Anyway, that's not a problem with chalk. As long as I have chalk, man, it is fine. Okay. So we talked about water. Now let's talk about ions. If you have something like sodium chloride, and drop it in water, the sodium chloride will dissociate. Have you ever gone to a party with your significant other? Are you there at the party the entire time together? No, you dissociate. You go off talk to your friends, your partner will go off talk to their friends. Are you there at the party together? Yes, you are. But you're not tied together. You're still free to distribute and roam as you like. Well, the same thing happens to what we call electrolytes. Electrolytes are just like regular electrodes, but they have 1/3 fewer calories. This sodium chloride, once it's in water, will dissociate to form sodium ions, where AQ stands for aqueous, and chloride ions. These are called electrolytes because, pardon my voice, puberty, you know. Salt. If you were standing in a big pile of salt and a high power tension line falls down in the salt, you're going to be fine. Salt does not conduct electricity. If you're standing in a puddle of very pure water, I mean very, very, very pure water, and a high power tension line falls into it, you're going to be fine because water does not conduct electricity. This is a major misunderstanding. Water does not conduct electricity. But the problem is, how often are you standing in a puddle of water that is very, very, very pure? Let's be honest about this. Even if it was pure, by the time you dipped your grubby little toe into that water, it's not pure anymore. Electrolytes are basically ions. They're salts. Salt is any metal and non-metal in its ionic form, so it doesn't have to be sodium chloride. But these ions do conduct electricity. And water. This is clean water. It has electrolytes in it. These will conduct electricity even in exceptionally low concentrations. So that puddle of water outside, it's not pure water. It has enough impurities in there that you really don't want to be standing near it if there's an electrical source somewhere, because it will shock you and quite possibly kill you. So don't try this experiment at home, because you will never get water to be pure enough. Okay? So, these are called electrolytes because they will conduct electricity even in very low concentrations. An ion is nothing but a charged atom. What happens here is sodium has one more electron that it actually wants. Chlorine has one fewer electrons that it actually wants. So unlike the partial charges that we talked about before, here that electron will physically transfer from the sodium to the chlorine. Once sodium loses that electron, it gains a fully positive charge because it's lost an electron. Remember, electrons are negatively charged. So you lose a negative, you get a positive charge. Chlorine picked up that electron. The electron is negatively charged, so it will create a fully negative charged ion. Okay? But opposites attract. Opposites attract. And remember, our water has a partial negative side and a partial positive side that I'm going to draw in between the two hydrogens here. So if we drop a sodium ion into water, which I want to show as a little circle with a plus sign, because it's an ion. If we have a sodium ion in water, what's it going to be attracted to? The hydrogen side or the oxygen side? Well, this is a positive charge. It's going to be attracted to the partial negative side of the water, which means the water very near the sodium ion, the water is going to align itself. It's going to surround that ion in what we call a water solvent sheath, like the sheath of a sword. It's going to create a layer here. Of highly ordered, or low entropy if you prefer, highly ordered water molecules. Entropy, by the way, thermodynamics, entropy is denoted with a capital S. So this region right here is a region of very, very low entropy. In fact, it's not just low entropy, it's very low entropy, because that water sheath will be held onto very tightly. Those water molecules are not going to flip around to give us hydrogens, at least to no appreciable degree, because the positive of the ion is going to be repelled by the positive of the water. Oxygen is glued right there. Far away where we have the bulk water, we've already talked about this. The bulk water has relatively low entropy relative to other solvents. It has a pretty low entropy because you have these regions of ordered water molecules. Now, they're only small regions, or little pockets, but still, towards the bulk water, we have low entropy. We have low entropy in the bulk water. Not as low as this sheath, which is very low, but it's low. It's low entropy. What about the water in between the two? We have a little bit of a problem here, don't we? Because we don't know, is the water in this middle area going to want to align itself with what's in this sheath, or is it going to want to align itself with the bulk water? We say that this water is undergoing what we call frustration. It doesn't know. Does it want to align itself with that highly ordered sheath of water, or does it want to align itself with the bulk water? Get far enough from this ion, it's the bulk water. Get really close to the ion, it's the sheath. But in between the two, we're talking a thickness of maybe 2, maybe 3 water molecules thick. We're not talking a great area here, but because of the frustration here, because it doesn't know how it wants to orient itself, this is very high entropy. That area of frustration is extremely high entropy. It doesn't know what it wants to do. We don't know what it wants to do. That's high entropy. So we have 3 regions. Very low entropy, very high entropy, and low entropy for the bulk solvent, or standard entropy if you prefer. So you drop this sodium into water. What's the net entropy effect? The net entropy effect is going to be the sum of the three. The net entropy is going to be the entropy of the sheath the change in entropy of the intermediate, and the change of entropy of the bulk water. Add those three areas entropy up, or change in entropy is what we're actually talking about here. Add those three areas up, that gives you your net entropy change because we have introduced this sodium ion into the water. Now the fact is, it is possible for the net entropy effect to go up or down, depending on the ion. Now it's not like you drop sodium in today, it's going to go up. You drop sodium ion in tomorrow, it's going to go down. It's not the way it works. But every ion, whether you're talking positive or negative, and we can talk about the anions as well, but here it'll be the hydrogens attracted to it. But it'll have a very similar kind of a diagram, only with these water molecules in the sheath flipped around. It'll be the same thing. But some ions are what we call structure makers. Structure makers, because the structure maker will have a total decrease in entropy, which means that this is going to way overcompensate for this. Or we have structure breakers, which means that this region, the frustration region, will overwhelm the sheath, and the entropy, net entropy, will go up because of the introduction of the ion. Experiment will show us which is which, but this is always possible. Now, we have introduced, let's talk about thermodynamics now. We have introduced the concept of ions and entropy regions based on if you're in the sheath, frustration area, or the bulk liquid. Let's talk thermodynamics, because in the second law of thermodynamics we get this equation. Change in entropy for anything, for any process. The change of entropy, at least for the universe, will always be greater than or equal to the change in heat divided by temperature, where Q equals heat. Q is heat. I found in the back of my freezer today, I'm having some financial difficulties, which means I'm eating leftovers from 2 or 3 years ago. But in the back of as my freezer starts thinning out, I found a bag, and I didn't know what it was. So I heated it up. Turns out it was a buffalo stew that I made several years ago, at least a couple years ago. And it's pretty good, but I didn't know what it was, so what did I do? I threw it in a pot, turned on the burner underneath it, and guess what? Heat. Q. I put heat into the system, which is my pot with the stew in it, until I could eat it. I'm happy I did it. It actually was delicious. And I have more than enough for the next 7 meals, because that's the way I've been eating these days. If I have food, man, I stick with it. Anyway, doesn't matter. It's a moot point. I applied heat, and I put heat in the system, delta Q. The change in heat went up, which means the change in entropy went up at least greater than or equal to change in entropy for my system went up at least as much heat as I put into it divided by temperature, or more. Okay? So as you heat it up, you're adding entropy. And then I stirred it up and started doing things like that. Some of the water evaporated and went off into gas. Well, that's going to add to the entropy. So the total entropy was actually greater than the amount of heat that I put in. But that's what it is. But now, we have a system where we are changing entropy. Just putting that sodium ion in water, or chloride if you prefer, or magnesium, or potassium, or fluoride, whatever it is, you put an ion in water, it perturbs the entropy. And I could rearrange this equation. I'm flipping the equation around, so I have to flip the inequality. Changing heat is always a change in temperature times delta S. That means that by the mere rearrangement of the water molecules, I am changing the heat. There's a relationship between heat and entropy, and I'm seeing it here. Now let's do a thought experiment. Let's take a tube of water. Our solvent here is water. We have our sodium ion here, which is either creating entropy because of its presence or removing entropy because of its presence. And let's put an imaginary boundary here. Let's just say, okay, well this is about half. Let's look at what happens when that sodium ion moves from this half to this half. Well, assuming that we're making entropy here, assuming we have an entropy maker, then dQ is positive. If we move this ion across this imaginary boundary, the side that the ion was on is going to lose some heat just by the mere fact of diffusion. Diffusion is the flow of ions from one region of high concentration to a region of low concentration. But because this ion is diffusing, it is losing heat. We're going to call that small heat quantity Q star. And when we put that ion on the other side, we're going to create entropy, which means that we're going to add heat to this side. And that exact same amount of heat is going to go into our solution on the other side. This is heat of transport. This is something that even most chemists have never heard of. I'm a theoretical chemist. I look at really strange things that most chemists just don't care about because, let's face it, this is not going to be enough heat to really be significant. We're never going to notice that. There's no practical use for it. But it's a fascinating thought experiment. Transporting ions, transporting anything, allowing diffusion to occur, it's related to a certain quantity of heat in so doing. It's going to drag heat along with it, unless it's an entropy breaker, in which case we have to reverse these two arrows because heat would go up on this side and down on this side, but in this case I'm assuming it's an entropy breaker rather than an entropy maker. So anyway, regardless, there's a little bit of heat associated with the movement of that ion. The reverse is also true. Dr. Lin, before he passed, he and his research groups were trying to find experimental evidence of this, and they were finding it. They took two plates, and they put high temperature on one plate, low temperature on the other, and they measured the salt concentration, the gradient between the two plates, because the exact opposite is true too. If heat is transferred with the ion, then heat can be used to cause the ion to move. We can actually influence where that ion is with heat. In this case, this is an entropy maker. or a structure breaker if you prefer, this likes heat. So if you put your hot temperature on this side, this is where the ion will transfer. Or if you put the hot plate on top, the ion will go towards the top. And you'll have a very slight, hardly, I mean, we're talking almost negligible. But that ion will move from the region of low temperature to the region of high temperature. Ladies and gentlemen, this is something you've probably never heard of. It's an insight into the behavior of ions and how it's influenced by something that has no physical, no tangible quantity. It's influenced by the presence of heat. It's never taught in a chemistry class because it has no practical value. There are so many facets of science that are never taught in a class. That doesn't mean they're not there. And it doesn't mean it's unknown, because we know about heat of transport. You can find Dr. Lin's papers on this. They've been published. So there are people who may know about this. Unlikely, I mean, the number of people who know are so low that it's unlikely any of them are watching this. If you are, I hope I didn't embarrass myself. Probably did. Anyway, but it's a fascinating thing. At least I find it fascinating, because you don't stop to think about the relationship between diffusion and temperature. But it has one. It does have one. And that's why I love science so much. There's so many things that we will never understand because we haven't thought about it. Science is nature is much more clever than we are. Anyway, I hope that you found this fun. Hope you found it at least interesting. And I hope you have a great evening. Thank you for watching. Have a good evening.